Hi everyone, welcome back. This is Dom Winski here again with you. I'm a research professor at the University of Maine, and we're going to continue to talk through the story that we're building about climate in Alaska and how that has changed over the past millennium and what that can teach us about climate in the future. So, I just want to bring us back to where we left off last time. So, if you remember in episode 2, we looked at snowfall in Alaska and how that changed over the last 1,000 years, give or take. So, we looked and we plotted the amount of snow that fell on Mount Hunter in the Alaska range over time, and we saw that there was a large increase in snowfall recently at about the same time as we started aggressively burning fossil fuels. So this could serve as potentially a warning because we might form the hypothesis from looking at this data that there's a link between human industrial activities and an increase in snowfall and the climate in Alaska generally. So what we're going to do today is to look at a parallel question having to do with the same ice core. And what we want to find is how much has the amount of snow melt changed since we started burning fossil fuel. We now have a good handle on the amount of snowfall, the amount of precipitation that falls, but what about the melting? What's the other side of the equation, and how much is actually melting of this extra snow that's falling? And what does that tell us about the climate system in the region? So before we get started, I think it's always a good idea to try and think through the problem and come up with some predictions about what you think the data might show. So if you get out your notebooks, I want you to start thinking about how much has the amount of snow melt changed since we started burning fossil fuels. And specifically, I'd like you to make a prediction. So again, in your notebooks, write something like, I predict that coring into the glaciers of Mount Hunter will show that since we started burning fossil fuels, the amount of snow melt has, and then you can fill that in with whatever you think your prediction is of how the amount of snow melting on this glacier has changed over time. And even better would be to think, to write down, I think this is because, and then you can make a hypothesis about the mechanisms or the causes of why you think snowmelt on Alaska may or may not be changing. So we'll take a brief pause while you write your hypothesis and your predictions down in your notebooks, and then we'll meet back as soon as you're done with that to talk about the actual data from the ice core itself. Okay, so now that you've had a chance to write your hypotheses and predictions in your notebook, we're going to dive into the data themselves. So here's the way we're going to look at the data. We have assembled for each of you a series of glacier core analysis models. So in each one of these models, we've put together images from the Denali ice core itself of one generation of melt data. So 25 years worth of images and pictures of actual melt features in the Denali ice core. So each core model is constructed from actual images of the ice core itself that we drilled in Alaska. And just like a regular ice core, we've put the oldest ice on the bottom, and then as you move higher in the core, the ice gets progressively younger. And ice cores are analyzed from the bottom to the top, and you're going to count each melt event as you go. And the melt events might be large and they might be small. And what we want you to do for each 25-year or each generation, we want you to go through and count the number of melt layers that have formed in the Denali ice core. So before we get started, we'll run through a couple examples together, just so you're acquainted with images of melt features in the Denali ice core and what they can teach you and what they represent. First, down near the bottom, we'll build this model from the oldest ice up towards the youngest ice, just as I previously said. So at the bottom, you can see a picture of the ice core, a real picture of the Denali ice core that we took in our laboratory. And that shows pretty smooth, featureless glacier ice, the normal kind that you'd expect to see in an ice core. There's no evidence of any melting going on here. But now if we add another image onto that, we can see this funny little dark band here. And this is what we're looking for. This is a melt layer. So this layer, you can identify it as a dark band of denser ice. And this would have formed from a refrozen lens of previously melted snow that would have formed on some very warm summer day long in the past. So what you can do is every time you see one of these dark bands like this, you know that must have formed when there were warm temperatures. So we'll go up some more, and now we can see this next photo up. There's not really any major melt features there either. And then above there, it's another just pretty clean glacier ice. And now there's a real thin feature right around here on your screen that you can see that was probably another melt event, though probably not as large as this one down here. And then lastly, a final photo showing some clean glacier ice. So this overall is going to serve as your glacier core analysis model for each generation. So if I were to count up the number of melt events during this generation, I would count two of them. The one really big one near the bottom, and then the one smaller one farther up near the top. So now let's get out your notebooks again, and then we'll set up a table so that we can actually start to record some of this data in a systematic way. So we'll set up a table and we'll title it Snowmelt During Each Generation, and we'll start it in the late 1700s. So there's going to be two columns in your table. The first column is going to be the generation end year. So that is the last year of each 25-year segment or each generation. So the first one's going to be 1800, then 1825, 1850, 1875, and so on, all the way up to the present generation, which ends in 2025. Now your second column is going to be the number of visible snowmelt events. So again, the theory is that the more visible snowmelt events that we see in the core, the warmer that time period likely was. So we're just going to count in each one of these core models how many melt events there were. We'll do, again, this first one together. So on the right of your screen, you should see a core model from Mount Hunter showing images that that represent the number of melt events we observed between 1776 and 1800. So let's count these. If I'm counting them, I can see three distinct dark bands of melt in this core. So there should be two near the bottom and then one up near the top. And each one of those, is a pretty large melt event. So we're going to enter in a number 3 in the top of the right-hand column of your table. So now what's going to happen is that we're going to go through each successive generation, and you're going to look at your ice core models and count up the number of melt events you see in each one. So we're going to leave each ice core model on for 10 seconds while you count the layers, and if you need more time, you can always just pause the video. So for each generation, just record the number of melt events and then enter that number in the second column of your table in your notebooks. And then we'll reconvene once you've had a chance to cycle through each one of the models and you get up through the most recent generation. Okay, so hopefully by this point you've had a chance to get through at least 1975 and have counted all the melt layers within the ice core models up to that point. So I'm going to write down here in my notebook what I counted, and hopefully that gives you a similar picture to what you've counted. And it's okay if it's not exactly right, as long as the picture is similar. So we're finding we have 30202, a small number of melt layers here in the 1800s, and then all of a sudden in the 20th century we start to get much higher quantities of melt forming in the ice core. And you can see in the most recent one, leading us to 1975, that it's actually really hard to even count the melt layers because there's just so many in the core, and they're getting progressively harder and harder to see. So to give you a sense of how we actually do this, since what you're using is just sort of a composite of images from the core itself, the actual ice core was very long. It's over 700 feet long. And what we did is we sent it through a digital scanning tool that created very high resolution digital images of the ice. And then we used a bunch of software to process those images and come up with various metrics to quantify the amount of melt in these layers. So that's what we did, and especially once you get near the top where there's so many of them, using those sort of computational techniques really improves the speed and the accuracy of making these sort of measurements. So what I'm showing you now is basically a data table of all of the different melt in the Denali ice core. And as you can see, as we scroll up and down, there's quite a lot of it. There's, at least a few hundred melt events sort of peppered throughout the ice core here. And most of them are up near the top in the most recent strata closest to present. I'm also showing you not only the depth that these melt events occurred at, but also the year in which they occurred and the thickness of each of those layers. And you have to do a bunch of different things to correct for biases about preservation for the melt layers, the amount of thinning that they undergo. But for now, we're just going to count them. And it turns out that between 1975 and 2000, there were 44 separate melt events in the Denali ice core. And now, finally, what we're going to do for the most recent generation, that is 2000 to 2025, is we have to estimate essentially the second half of that generation, because this core was drilled in 2013, which means we only have data from the year 2000 to the year 2012. So now we're going to count the number of melt layers between the year 2000 and the year 2012, and that turns out to be 53. And then we're going to multiply that value by 2, figuring that the amount of melt between 2013 and 2025 carries along at about the same rate as it has in the early 2000s. So when we multiply that by 2, our estimate for the amount of melt layers formed in Denali during this present generation is 106. So now that our table is complete, our next step is going to be to actually plot and make a graph of the data. Since I think oftentimes making a graph of your data, just like it did in the last exercise, can really help drive home the main message that you're getting from your data set. So on your screen, you can see a plot that I've set up, and I suggest you get out your notebooks and make one that's similar. So on the x-axis, you can put the year, specifically the last year of each generation, along on the x-axis between 1800 and 2025. And then on the y-axis, you can set that up with the number of snowmelt events that are occurring during each generation. And then you can go along and you can plot each one of your data points along in the graph. So take a moment to do that, and then we'll meet back as soon as you have created your own plot. Okay, so by now, hopefully you've had a chance to plot the data in the graphs that you made in your notebook. And now I'll fill in my plot over here. And as you can see, the amount of melt stays very low. There's just a few events per year up until around the mid 20th century. And then all of a sudden, it really takes off and accelerates to over 100 melt events per generation. That's more than once every year. It's really a common thing to have melt at this ice core site now, where it used to be an incredibly rare event. And just for context, I'm going to put in this smokestack on my graph that showed that around the turn of the last century is when we really started to ramp up our industrial activities as a planet. So I want you to now start thinking about this data and what it might represent. So again, in your notebooks, before I start to give you my own interpretations, please write down 2 things that you notice about the data, and then 1 thing that you wonder. And then once you have written down 2 things that you notice and 1 thing that you wonder, we'll meet back and then start some discussion about the Denali ice core and what we might learn from it. So by now, hopefully you've had a chance to write down 2 things that you notice about the data and then 1 thing that you wonder. And to further this discussion, we're also going to think about our interpretations of this data. So in my notebook, I'm now going to write, the data suggest that since we started burning fossil fuels, and then you can finish that sentence with whatever you observe about the data. And then also what's good, because you always need evidence to support whatever your interpretations are, you can say the evidence that supports this is, and then you can introduce whatever you think the evidence is to support your interpretation of the data. Okay, thank you all for writing down your interpretations and the evidence in your notebooks of what you think these data mean. So to finish this off, I'm going to now talk about what I think these data mean. And in order to do that, I'm going to bring us back to the data that we collected back in episode 2. So I'm going to bring in the snowfall data from Mount Hunter in addition to the snowmelt data that we just plotted now. So 6 years ago, I was a student, and I was looking at these data just as you are now. My colleagues and I were really curious about what it was that actually connected all of these data sets. So as Mikhail and I have mentioned previously in this series, it's really important to look at all the data as much as you possibly can when you're trying to solve these problems, and that's what we did. We brought in weather station data, output from climate models, other archives from ice cores, from tree rings, from corals, anything we could think of to try and solve this problem. And eventually, we think we did. It turns out that the key to this mystery lies thousands of miles to the south in the tropical Pacific Ocean. So this region of the world is incredibly important because it contains an enormous amount of heat and energy that can influence the climate systems in regions around the globe. And that's exactly what's happening here in Alaska. So with progressive warming in the tropical Pacific during the industrial era, that has set up this system of climate anomalies in the Pacific that's transmitted to Alaska and leads to these extra influxes of heat and moisture and air into the Alaska range where our core is located. So as the tropics have warmed, that has led to an increase in heat in Alaska, which is then reflected in our ice core as an increase in melt layers. And then, again, with the warming tropics, that has led to an increase in moisture coming into Alaska, which is then recorded in our ice core as an increase in precipitation. So in this way, we find that these data sets, this increase in snow melt and snowfall, have their links all the way back in what's happening thousands of miles away in the tropical oceans. The other thing I want to bring up is that it seems like, well, maybe this will all cancel out because we're having more snow melt, but we're also having more snowfall. So maybe that all works out. But in fact, it doesn't. The amount of extra snowfall is not nearly enough to compensate for the amount of extra snow melt in Alaska. So in fact, the glaciers in this region are rapidly melting, so rapid that the extra amount of snowfall is not nearly enough to keep the glaciers in this area from disappearing. So this is still an incredibly urgent and important issue to study because, first of all, these glaciers are not going to be here forever, so we only have a certain amount of time to capture these valuable records. And then second of all, the loss of these glacier systems is going to have incredible impacts, not only for people who live in Alaska, neighboring Canada and Siberia, but also worldwide as it winds up feeding into the amount of sea level rise that we're experiencing globally. As we conclude, I just want to emphasize the importance of these data and what it can show us about the Earth and where we're headed as a planet. Both of these data sets, both the snowfall and the snowmelt data set, are showing us that something really crazy and unprecedented is going on. The levels of snowfall and snowmelt are something we haven't seen in at least a millennium, and it's happening right now. So we really have to look at whatever warning signs are happening either from this ice core or other records from around the world, and really pay attention to those things and try and learn from them before the changes that we're experiencing become sort of more than we'd like to put ourselves through. So that said, I'm still optimistic about where we're headed and the potential for our planet's future. I think as long as we remain curious and committed to being able to solve these problems and understand more about our Earth system, and then apply that understanding towards creating solutions, that we have the potential to really succeed as a society and into the future. So I just want to finish by thanking all of you for taking the time to work together with me on these data. I'm really excited about it, and I hope that you've learned from it and have enjoyed it. Best of luck.